going to do an example problem of uniform circular motion. So my really good friend next door just learned how to ride his bike. And his older sister is already an expert bike rider. And we have this small little hill in the middle of our cul-de-sac. So the older sister, we'll call her Sarah. Sarah rides her bike really, really fast. She goes over this hill in the cul-de-sac and loves to fly off the hill and land really far away. Well, her little brother, who just learned how to ride his bike, he wants to be just like his big sister. So what does he do? He goes pedaling really, really fast, but all he does is go up and back over, not getting the clearance clearly that the older sister Sarah got. So what would, we'll say his name is Sam, what would Sam have to do to leave that hill? How fast, what does he have to go to launch himself into the air? So we can actually model this as a way of uniform circular motion, and we can ask the question, what minimum speed does Sam have to have in order to leave the hill at the very top? All right, we need to know a little bit of information. One is, how's the hill like a uniform circular motion, a circle? Well, if we imagine that this hill, that's not a good color, it's actually the top of this hill, the crest of this hill is part of a circle. We're going to say that that hill has a radius of 3 meters. So if I just look at the very crest of this hill and model that as a part of a circle, a secant of that circle, then I can look at this as a uniform circular motion problem. All right, so let's say that Sam has a mass. He's only 4 after all, so we'll say he has a mass of 30 kilograms. All right, so how fast does Sam have to be going in order to lose contact with the hill at the top? Well, with any circular motion problem, we have to do a force analysis. So we first have to identify our object. Well, our object, also not a great color, is going to be Sam. And since we're looking at forces, we're going to do a force analysis. So let's look at the forces that are acting on Sam as he's biking on this hill. And we're going to take that right at the very top. We know that there is the force of gravity, so we have the force between Sam and the earth. And I'm going to draw my free body diagram over here. So the force of gravity we know points straight down. That equals mg. Okay, and it's also known as the weight. Sometimes we like to remind ourselves of all of those ways that we describe the force of gravity so that we don't lose sight of that as we're reading problems. And what else? Well, Sam could be interacting with the hill. So for the case of him just going up and over, he still remains in contact with that hill. And so because of that, there is a normal force acting on Sam in connection with that hill. All right, well, Sam's pushing down on that hill, so that normal force is pushing up. So we know that there's a possibility of this normal force. So Sam just goes up and over. He glides. He's not pedaling. He's not propelling himself. He's just going at a constant velocity up and over this hill. So there's a normal force and the force of gravity. Now, if we want Sam to lose contact with that hill, well, what happens to the normal force? It goes away. And so in the case where Sam just loses contact with that hill, well, then there is no normal force. So the force of gravity is really the only force acting on him. All right, so let's now continue with our force analysis. We just have one. So we're going to only look in the vertical direction. We have nothing happening horizontally. And we know that the force of gravity is acting in the vertical direction. It acts in the downward direction, so we put that negative in there. Our next step is to analyze which direction the acceleration is happening. Well, we only have one direction, so it's got to be in the vertical direction. And what type of acceleration is it, linear or circular? Obviously, we're doing a circular motion problem, so it's going to be a circular acceleration. Now, if Sam's just leaving, of course, he's not going to remain in uniform circular motion. So what we're really asking is, what is the absolute point, the absolute force that would happen for him just to stay on the hill, which is the same as the absolute force that he just leaves the hill with. So we're going to look at this as a uniform circular motion problem, where the sum of the forces is mv squared over r. So we add these forces. R is only one, so we have minus mg equals mv squared over r. And we want to remind ourselves that that's the magnitude, so we want to consider direction. We're being very explicit about direction in our list, so let's maintain that being explicit about direction. And we know that if the circle is a vertical circle and Sam's at the top of it, then that sum of those forces is in the downward direction. So now all we have to do is solve for how fast Sam has to go in order to leave that hill. So doing a little algebra, my two masses cancel out. My negative goes away. We're going to solve for v squared. So we have r times g is equal to v squared. Take the square root. And square root of r times g is equal to our speed. So we can look at that. We said our radius was 3 meters times 9.8, that force of gravity, that acceleration due to gravity. Take the square root. And Sam would have to be going 5.4 meters per second in order to just maintain contact with that hill or to just escape it. So we know his sister clearly goes faster than that. All right, so uniform circular motion problem, we can model areas of a circle as uniform circular motion if we are indeed going at a constant velocity or at a very specific velocity at that point. Identifying that object, looking at the interactions, recognizing in this case that there would be a normal force when Sam goes up and over, but in the example that we're trying to solve for, what is that minimum speed? What is the very smallest normal force? 0. That can get us just up and over, or him escaping. Recognizing the direction of that acceleration, which is in the vertical direction. Recognizing that acceleration is indeed uniform circular, centripetal acceleration. So utilizing our relationship for the net force when we're dealing with centripetal motion, and then solving for our velocity. All right, good job.